Okay, good afternoon. Let's continue our lecture on feedback control for discrete system. Last time, you learned how to design a controller for a system. For the state feedback, for state feedback only, you learn the process to choose the controller K, and for the state feedback with integral, you use trial and error method for the integral action controller. Actually, one step that is very important even before you start designing controller is to check controllability. Because if your system, the nature of your system is not controllable, it does not make sense to start to do controller design. There won't be any good controller for that. So you see the term controllability. Controllability. So there must be a relationship between the nature of the system, dynamic of system, which is defined by the coefficient phi, and the ability to control, right? So of course the coefficient gamma has to be involved, because it defines what value of u. Because let's say you have 3 dimensions, but you only have only one non-zero element. It means it's less likely that you can control, right? It's less likely you can control the system because you only have one action on the first equation. Okay, see? And also, for example, the more control variable you have, the more likely you can control your system. Okay? So for example, if you have like this, you have three controller, right? So you need the U1, U2, U3. So this case and this case, let's see, this case is more likely you can control your system because you have more freedom on the input. You can generate input from U1, from U2, and from U3, right? And so this case you only have one action for the input and only for the first equation. Perhaps the second equation, second state or third state, you are not able to control it, to control them at all. So that controllability defines as a function of gamma and phi in this way. And you can control the system if this matrix has full rank. Okay, has full rank, or you can sometimes you see the terms non-singular, which means determinant of this matrix is not 0. Okay. I think we should try one example that we have before. Let's say the matrix, let's say a matrix phi equal to, okay, not exactly the same example before. Let's say matrix phi is like this, and gamma is like this. 1, 2. Then we can find C equal to, first you use gamma 1, 2, and then phi times gamma. Phi is like this, 0, 0, 2, 0, times 1 2 like this, right? So you have 1 2 and this one, this time this you have 4, and then this time this you have 0. So clearly the determinant of this one is not 0, which means your system is controllable. Okay, after you check that it's controllable, then start the process to find the controller. Okay. Today's main objective is to show you how to use place for both continuous system and discrete system. You will see why we can use only one command, but it can be applied to both continuous and discrete. Now let's look at the comparison here from the equation themselves. For the continuous one, we have state equation like this and output equation like this, and we can use state feedback u equal to minus k times h. This is state feedback, right? And for discrete system, okay, actually we can transform this one into discrete, and then we apply state feedback which has the same form, right? Then we can substitute the input into the original equation here, like here, and finally we can use Laplace transform. So from here to here we use Laplace transform. Then we can have the characteristic equation by setting determinant of this matrix to be 0. Okay, so you can have equation in terms of S. It can like S, for example, if it's a second order system, S squared plus AS plus B equal to 0. Okay, how about this one? When you have a discrete system and you substitute the input, control input by state feedback into here, right, from here, and then you use the Z transform of this equation, right? You use Z transform, then you get this matrix which actually has the same form of this one, right? You just change from S to Z, see? Which means actually you can get characteristic equation from here. It's second order, it can be just Z squared plus ADZ plus BD equal to 0, something like that, right? So from here you can see that, well, actually we can easily use the algorithm place the poles, right? We select the poles for the characteristic equation, and then we find the controller gain k. Okay? So here we choose poles. Oh, I'm very sorry about the capital letter, or just use lowercase like this, right? Okay. All right. So you select the poles like here. Pole can be an imaginary number. That's why I define imaginary parts equal to square root of 1 times 2. Okay. And then you have pole. The poles must be complex conjugate. That's why you choose this one. In this is example, it can be third order. It has to be third order, right? Because we have one pole here and then two complex pole conjugate.
Why one of the pole is not complex?
Sorry?
Why the first pole is not complex?
If third order, let's say let's say s plus as square plus bs plus c equal to 0. So one root must be real. Yeah, something like that. And if you choose your pole to be complex, there must be pair of poles to be complex conjugate from this polynomial equation. Same form for this, but the difference between continuous and discrete is that the value of pole itself, to have your system stable, you must choose negative real part, see, for continuous system. And for discrete system, you must choose the norm of the poles, let's say ZP, or maybe just say, ZP pole. The norm has to be less than 1. Yeah. So that you can have the controller gain K for your state feedback control system. So this is the block diagram. I try to draw the most the simplified one, not the full one that I assume that D equal to 0, okay? 0 vector. So I don't need to use D. Okay? This is state equation. From state equation you have H dot here, and then you integrate, you get H, and H times C, you get the output Y, right? And you use state feedback, which means X here time K, so you get KH here, and minus is here. Alright? Right, so this must be U. And KR is the scaling coefficient, yeah? Scaling coefficient for state feedback. To have the final goal Y of t tends to R of t. This is the goal. For discrete, where you have function hk plus 1 equal to in function of hk. So here you have hk plus 1, and it passes through unit delay. Then you got hk here. So hk here, you use state feedback, it times k, and then minus here. So here is u. All right, and u. So inside u must multiply by g to have hk. Yeah, to compute this, and then you get hk plus 1. Same, kr is scaling factor. Okay. Any question here? So now let's do one example. Look at the example. You have double mass here, mass 1, mass 2, denoted by capital M and lowercase m, and you add the input on the first mass as a force. So the force push M1, and then M2 here must have motion as well, but it depends on the flexibility characteristic of this joint, these links. Then the motion could be, very dynamic. Okay. Then the equation derived from this model to be like this. So there are two state variable. I would say all right. Sometimes we are interested both y and d. We want to control both y and d. Okay. Let's say we want to control both y and d. Then, but we only have input u. U here. So is it possible to control the whole system? Yeah, controllability we only check on the state equation, right? Actually, right? So okay. So in this example, first derive its state space representation. So to warm you up, I want you to try first. Okay. I give the hint because in here we have displacement y and d. So you have 4 states, right? If you only have one mass, you have 2 order system, right? One mass, and now you have 2 mass, so it must be 4 order. Yes. So I can give you state h1 equal to y, h2 equal to y dot, h3 equal to d, and h4 equal to d dot. Okay. Then you derive the state space representation. Actually, the first 2 equation has to be h1 dot equal to h2, of course, and then h2 dot equal to something, and then h3 dot has to be h4, right? This one 3 and 4, and then you find h4 dot equal to something. Right? Yeah, so now you start by yourself. Okay, so for number 2, assume that the resonant mode has frequency 1 radian per second and damping ratio 0.01. And then select the ratio of mass to be 10 to 1, which means capital M equal to 1, and then M equal to 0.1. B to be this, K to be this, and pick the sample time to be 15 times faster than the resonant frequency, right? So first, A, check the controllability. So now you already have the parameter, the value of parameter, then you check controllability. Then transform the continuous state space into discrete state space. Okay. For B, you need to choose the sample time properly according to this instruction. But now please check controllability. So to check the controllability, actually we can immediately check it on the continuous system using this form h dot equal to sh plus gu, and then the controllability matrix C equal to this. You got G, and then F times G, and then F square times G. So it depends on the size of the F. Let's say if you have 4 by 4 matrix of F, then you need this term as 1 kilometer, this is second kilometer, this one the third kilometer, and then you need another one as a 4th kilometer. So you have a square matrix. Then you apply determinant. If the determinant is not 0, then it has full rank. Okay. So I suggest you use Scilab or MATLAB. Okay, so first we define our parameter B, K, omega n as natural frequency, and then period in terms of omega n, and then the sample time is 15 times faster than the resonant frequency. So faster means, look, I think I made a mistake. Faster means sample time should be shorter, right? Frequency faster means more often, frequency high, so sample time should be small, so it should divide it by 15, like this. Okay, and then you can, okay, anyway, I think for the continuous time you don't care about sample time, right? So you just need to use all these parameters to define the matrix F. So what is F? You already found. So here we can define the matrix F and G. After that we construct controllability, maybe just say CO and T. Alright, first you have G and then F times G, and then F times F itself and times G, and then F times F itself times F itself times G, right? And then we find determinant of controllability matrix, and we want it to display. Let me run it, and then let me check in here. What is this? Oh, this one. Okay, let me try again. Save and execute. We don't see the determinant here. Okay, let's try determinant of CO and T here. Okay, it's not 0, which means the system is controllable. Why this one does not display? Let me say, not constant, it's controllability. Controllability matrix. Okay, controllability. So whatever, you can just say C, but sometimes it can be confused with your continuous system y equal to CH. Oh, this? Yeah, all of these, right? Yeah, from the theory here, but I did not prove. Okay, you can just refer to this, or to this. Yes, controllability. And actually C, yeah, I think it's confusing here. You have C here and also you have C here. That's why I changed to be like a controllability matrix. Just call it CON, right? Yes, CON. Yeah, so just say ON here. And then I call here determinant of CON equal to this, right? Okay, like this, and then display determinant of controllability. Yes, like this. Okay, like this better. Or maybe just say like this. No need to have too many lines of code. Just like this. Okay. Con is not correct. Why it can read eyes? I see. Yep. Okay, so the next point, transform the continuous state space into discrete state space. So you have tried this before. Now let's do it again, but with our new system. So in order to design a controller system for this multiple input, multiple output, we need to check the dimension of input and output. So because we only have one input, right? Then we are able to control only one output. So in this case, either you control the displacement D or displacement Y. Let's say you want to control Y, then you choose C equal to C, not this C, this ON, CON, DC. You choose it to be 1 0 0 0, because when C times X, you times X1, X2, X3, X4 will be just X1, which is Y. Okay.
Sorry, I'm still not sure about that.
Okay, so the syntax of transforming the continuous system into discrete system is DSCR. So first you define continuous system. The input is A, B, C, D, but actually in here we use F, G, H and J instead. Now we already have F and G, then we need to define okay, sorry, so I need to change it accordingly. F, G, H and J, right? So I use here I use H equal to, because we can, let's say we want to control output Y. So Y is X1, so we use 1 0 0 0, right? And D, because we don't have direct from D to output, then D is 0. Okay. Why I say D? It's supposed to be J, right? Yeah, J here. So we can define linear system, and then we transform into discrete. But here discrete we use sample time TS, which is 15 times faster in terms of frequency, right? Yeah, faster in terms of natural frequency omega n, right? Okay. After you have a discrete system, okay, let me display discrete system sys D. So when I run this, what can I have from the display? Run it, save and execute. Here it is. So linear state space A B C D H0 T, and it say A B C D again. So where is A 4x4. I guess I need to use a different syntax. I mean, we should have the return like phi and gamma. So let me go to help. Discrete DSCR here. Can we have phi and gamma? No, we can't have. We can't have. So actually F here. Yeah, where is F? A, B, C, D. I'm not sure with this arrangement. Well, so in order to define phi, we use display is not good to use here. Matrix phi equal to system discrete like this of 2, and then gamma equal to system D of 3, and then gamma 3, and then 4 J, yeah, and then H equal to system D of 4, and then J equal to system D of 5. Okay, and what else do we need? 6 initial state. We don't need to specify it. So from here, from here it means we already transform. We already transform from continuous to discrete, and we have all the necessary parameter phi, gamma, H, and J. This means that we already complete question B of 2, right? Yep. And then for initial condition D equal to 1 meter, show free response of 2 cases. Pick all poles at this one. Pick all poles at 0.9. It means we have 4 states, and then the characteristic equation is supposed to be 4th order, so we can have 4 poles. So in here you use the syntax anchor for pole placement. Instead of place, you use this one, because this one can handle duplicate poles. If you use place, you cannot use this pole, I mean double roots or triple or four root, right? Just to be aware. So actually to be safe, it's better not to choose the same poles, at least slightly different. And then you can use place all the time, because place can use with the higher order as well. For the A curve from Ackermann algorithm, it can have good performance from the fourth order or less, okay? Fourth order or less. Alright, so try try two cases, A and B. So let me check for ITC-DCLab. Does it have acre? Yeah, acre syntax. AC. It doesn't have, right? But it does have place. So it does have place. Where is it? Okay, call it pole placement. Okay, pole placement. Here. This one, P pole. Right, it uses P pole. In MATLAB you use place. Okay, let's try with this one with double pole. I'm not sure if it works or not. Oh, what happened? Okay. What should I do? I'm a little bit lost, sorry. We try here first. Here. So first we select poles equal to 0.9, 0.9, 0.9, 0.9. Okay, and then we define k equal to p pole of phi, gamma, and then pole. Let's see whether it's implement Ackermann algorithm or pole placement algorithm.
Why are the poles
Sorry?
why are the poles equal to 0.9?
Oh, because in this problem it say
Okay.
peak order pole 0.9. Anyway, you may try different value as long as less than 1, because you want to have a stable system. Then let me display k. Alright, so actually we can design k. Yeah, we can get the value of k. Look, k should be 1, 2, 3, 4. Yeah, that's right. I have displayed here as well, right? Okay, let me comment this one. I don't want to see it to avoid confusion. So if I run again, let's say clear. Okay. All right. So this is the value of k, and what you can do next after you get K for A, case A. Okay, now let's try case B. Okay, B, you define poles with different value. Now use poles. Yeah, you can copy this 3 line, Control C, Control V. We pick the pole and then we should simulate the feedback system, right? Yeah, actually case A has not been finished yet because we don't see the result of feedback control yet. For the feedback control, I suggest how say we use. Yeah, actually we need to build a block diagram for the feedback control to see the performance. Once you have K, and then you need to build a feedback control in the block diagram model, right? You have built before actually. Now you need to build it to complete the question A of 3. Okay, let's say let's say I finish the model in the block diagram with the Z codes of Scilab or Simulink of MATLAB. Then I go to question B, just try with different poles first. So for example, this one is 0.9 plus square root of 1 times minus 1 times 0.05. It's too long. I think I repeat. Yeah, I think I just say I equal to square root of minus 1. Okay, then here I say I times 0.05 and then 0.9 minus I times 0.05. Okay, and then this one 0.8 plus I times 0.4 and then 0.8 minus I times 0.4. Yeah, 4. Okay, like this, and then define K again. Let me run. Right, so this is the value of K, right? So from these two cases, maybe this one I should use K1 and this one I use K2. Then you can use these two value for building the simulation using block diagram. Yeah, something like this. Then you can compare the result for these two cases. Yeah, so I'm going to explain how you build a Simulink model in MATLAB. Layout blank. So first you start from the dynamic model because we are going to use a discrete model. You use block MATLAB function, which means you define hk plus 1 equal to phi hk, hk plus gamma uk. So in here you write code, right? You define phi equal to, for example, phi equal to, you have seen before, and then gamma equal to, but before you get phi and gamma, you have several steps, right? Like this, and then you can write down, just write down you just write down k1, maybe, it's just notation. So hk1 equal to phi times hk plus gamma times u. So u must be input here, uk, right? So here is hk plus 1, and then you use block unit delay, you get hk like this. Then this hk you need to use it for feedback here, okay? And right, so this for this function, it start from, actually it start from function, then name hk1 equal to FCN of input uk and hk, but maybe k not bottom like this, then you have several lines like this one, right? All of these, and then not this one, 666, this one, all of these, and then you get phi and gamma, right? From the top here until here, okay? For the function, right? You just need the phi and gamma, but you need everything above. You may not need the controllability because we already checked. Then you have the output for this function. You have the output for this whole block. This is just image. This is just image. It's not something that you write in the code, right? This is the actual code, right? So this means the output this is output. So you define from here. Then how about u? What you can find u here, you add block add and plus a minus, add, you can put add here and then minus here, and then you get from it's from maybe like this. It's easy like this. You get u from here, and then you use gain k. For the case 1 you use k1 plus minus, and you must use matrix multiplication. right? This value K1 has to be the exact K1. So how you can find that K1? Oh, yeah, you can write all of this in another script and run it to get the value K1 in the workspace, right? So you can use K1 in here, and this one you need to find KR. So that you can set the reference here RT, and here is no, let's call it KR or K, right? And this one, in order to see the result, you use scope. Yeah, so actually very similar to Scilab Z codes. It's just the way you write function is a little bit different. In order to open the editor for the function, for this one you just double click on the MATLAB function block, right? From user define function. Yeah. Okay, so we will continue next time, and you will see how you try at home first, and you have any question you can raise during the next session, and then I will complete all the model in the Simulink.